Okay, I think we're good. All right, so then that other question, number 16 on section 7, let's look at this one. For what values of x does the series below converge? What is its sum? What series do you get if you differentiate the given series term by term? And then for what values of x does the new series converge? What is its sum? Okay, so for a question like this, you could write this out in the other format. So remember the long format here, n equals 0 to infinity. It'd be that negative 1/3 to the n and then x minus 4 to the n. This is going to be a power series because it has the x inside of there. It's also a Taylor series, kind of weird Taylor series, but we can ignore that because it's not really what the question's asking. The question's only asking is to figure out where does this thing converge. Anytime you have a power series and it's asking you where does it converge, you could either do the ratio test or you could do the root test. I almost always do the ratio test because that's the one that works most often, so I'll just do the ratio test here. Remember, the ratio test is the limit as n goes to infinity of the n plus 1 term of your sequence divided by the nth term inside of an absolute value. So for us, the limit as n goes to infinity of the absolute value, the n plus 1 term would be negative 1/3 to the n plus 1 times x minus 4 to the n plus 1. That all divided by the nth term, just negative 1/3 to the n, and then that x minus 4 to the n. All right, so just always write it like that, right, with the ratio test. The n plus 1 term on top divided by the nth term. If this was a fraction, then you could do that trick that I showed you guys where you write the n plus 1 and then multiplied by the reciprocal of the second. We don't have that going on here, so I can just ignore that. We are going to use a similar trick that we almost always use with this ratio test. I have n plus 1 exponents on top and just single n exponents on the bottom. I can think of this negative 1/3 as being a negative 1/3 to the n times a negative 1/3 to the 1, which means that the negative 1/3 to the n is going to cancel out on top and bottom, but I still have just a lone negative 1/3 to the 1 floating around. Same thing is going to happen with the x minus 4s. X minus 4 to the n cancels, but I am still going to have a lone x minus 4 just to the 1 power floating around. All right. Notice that there are no more n's inside of my limit, which means that the limit as n goes to infinity is just going to be this constant on the inside, constant with respect to n. Absolute value of negative 1/3 is positive 1/3. Absolute value of x minus 4, because we don't know what the x is, we're going to write as absolute value x minus 4. This is what the limit of the ratio test gives us. Don't forget that this has a name to it. This is what we call rho. This rho has to be less than 1 for the series to converge. So rho must be less than 1 for the series to converge. That just comes from the definition of the ratio test. So we don't know exactly what our rho is because of this x value, so what we're going to do is we're just going to force that rho to be less than 1. We can multiply the 3 over, and now we have an absolute value that is less than something. Absolute value inequalities, you always do the same way. You're going to squeeze the inside of the absolute value between the positive and the negative of the other side. Finally, if we just add the 4 over, we get this. 1 is less than x is less than 7. The only other thing that you have to worry about is you have to worry about the end points, whether 1 or whether 7 is going to be convergent. Everything else we now know. We now know that everything in between 1 and 7 does converge. Everything outside of positive 1 and 7 is going to diverge. So let's check the endpoints. Let's first check that left endpoint when x is equal to negative 1. Not negative 1. X is equal to positive 1. To check an endpoint, what you want to do is you want to plug it back in to the original series. So we're just going to replace this x with positive 1 and see what happens. So then it's going to be the infinite sum, n going from 0 to infinity. We still have the negative 1/3 to the n, but now we're going to plug in 1 for that x. So it's going to be 1 minus 4 all to the n. All right, 1 minus 4 is negative 3 to the n. So we have negative 1/3 to the n and negative 3 to the n. You can just multiply those two things together on the n side, which is going to give us 1 to the n. But 1 to the n is always just going to be 1, regardless of what the n is going to be. And if I just add the number 1 an infinite number of times, it's going to blow up to infinity and diverge. Cool. So that says that this endpoint is not going to work. Let's try the other endpoint, x is equal to 7. Plugging that back in, it's going to be that negative 1/3, and then it's going to be 7 minus 4 to the n. Now I have negative 1/3 to the n and positive 3 to the n. Again, you can just multiply those together. That's going to be negative 1 to the n. This just alternates positive 1, negative 1, positive 1, negative 1. That series also diverges. That means that neither of my endpoints are going to work. Just the inequality 1 less than x less than 7. So if I go over to the homework here, the series converges in a compound inequality 1 less than x less than 7. Okay. The next part of the question is asking you to find the sum. The only time a question will ever ask you to find the sum of a series is if it is a geometric series. And this is a geometric series, so just to write it out again, n equals 0 to infinity, negative 1/3 to the n, x minus 4 to the n. This mimics our geometric series, n equals 0 to infinity, a r to the n. It's not quite written the right way, but we can easily write it the correct way. So we can just multiply these two things together because they are both to the n power, and our a is just going to be 1 since we don't really have a coefficient. So we have a 1 out front times negative 1/3 x plus 4/3 all to the n. All right, so this was just distributing the negative 1/3 into the parentheses here, because they're both to the power n. The 1 is out in front just to mimic our a. So now from the geometric series, 1 is going to be a, and then our r value is going to be this awful looking thing. Okay, so to figure out what that awful looking thing converges to, remember that the geometric series converges to a over 1 minus r. So it's going to be 1 over 1 minus negative 1/3 x plus 4/3. All right, I know my handwriting's pretty bad. Try that again. 1 over 1 minus negative 1/3 x plus 4/3. There we go, that's a little bit better. We can multiply everything by 3 here and then distribute some stuff around. Let's go ahead and combine the like terms. So this negative on this positive is going to be a positive 1/3 x, and I have a positive 1 and a negative 4/3, so I have a negative 1/3 floating around. Now I can multiply everything by 3. I get 3 up top over x minus 1. So the question is asking, well, what does this power series converge to? It converges to 3 over x minus 1. The next part is saying what series do you get if you differentiate the given series term by term. Just take your nth term here, this, I can't highlight it, but this part, and take the derivative with respect to x. So if I do take the derivative with respect to x, negative 1/3 to the n is just a constant. This is going to be a chain rule. We're going to bring down the n, take 1 away from the exponent, and then multiply by the derivative of the n side, which is just going to be 1. All right, so the negative 1/3 of the n stays, so it can't be a. We have just an n that comes down, so now It's either b or d, but we do have to take one away from that exponent. So it's going to be n minus 1. So this has to be b. It's asking where does this new series converge? Whenever you take the derivative or the antiderivative, the convergence is in the same location as the original series. So if the original series converged between 1 and 7, the derivative series is also going to converge between 1 and 7. The last step here is it's asking what is the sum of this new series, this new derivative series. It would be very, very difficult to figure out what the sum is based on the series, but luckily, we know what the original series converged to, so we should be able to figure out what the derivative series converges to. It would just converge to the derivative of the previous limit. So we can just take the derivative of this thing, which would be -3 over x minus 1 squared. And then that's going to be the sum of the derivative series. Whew. Throat's hurting now. Does that one help? Does that make sense for this question now? Okay, awesome. Did anybody else have any other homework questions you want to look at? Okay, let's get away from homework. You do have the chapter 10 test that is due this weekend. So let's pull up this practice test here and let's look at that. I think this was the practice test that I pulled up last time, but I only did like 1 or 2 questions. So I don't know, how do I want to do this? Oh, I do want to warn you a little bit. This test is not one that I had made up. This was a test that I had found online. So only some of these questions are going to be pertinent to you guys. So let me just tell you the ones you can ignore. You can ignore number 12 here. Definitely don't do that one. You could do 11. That's pretty cool. 10, don't do 10. That one's too hard. I think the rest you could do just fine. All right, so 10 and 12, ignore those. Okay, so let's just kind of go back up. Let's start at maybe number 4 here, and let's work our way down. Okay, remember that you guys have a lot of tests to determine whether a series is going to converge or diverge. I sent out an email, this was a week or 2 ago, that had like all of those tests in just a single kind of worksheet, all organized. So I'd recommend having that in front of you whenever you go to take the test. But a lot of the times on actual test questions, I'm not going to specifically say use this test. I'm just going to ask, does the series converge or not? And then either it'll be multiple choice. You've seen homework questions that are like this, where it has like a bunch of the different tests and the reason why it converges or diverges. Or I'm not really going to give you an option. You're just going to have to kind of fiddle with it and determine which test to work, which would work best. Okay, but on this practice test, it doesn't really give you an option. It just says to use this. So this first one is asking us to use the limit comparison test. So let's talk about that. And we're given the series n equals 1 to infinity 8 over 6n plus 5 square root n. All right, the limit comparison test is when you want to look at the ratio of the limit of the sequence values of 2 different series. Depending on what that limit goes to, it gives you some information about the 2 series. You always want to pick a series that behaves very similarly to the series that you're given. if it's polynomial stuff or fraction stuff like this, the thing that you want to try is you want to try based on whatever the leading terms are for the numerator and the denominator, and you can always ignore constants. So 8 over 6n plus 5 square root n, my numerator doesn't have any n's at all, so I'm just going to let this, this guess series be a 1 up top, just that constant. In the denominator, I have a linear term, and then I have this square root term. As my n's start going to infinity, this 6n term is going to take over, and then this is just going to go to the wayside. In other words, I can kind of ignore this 5 over root n term and just think of the denominator as being a linear function. The 6, again, we can ignore because that's just the coefficient out in front, and coefficients aren't going to really change anything. So what I'm going to do is I'm going to take this series that I want to know whether it converges or diverges and compare that to the series 1 over n. This is the harmonic series. Don't forget that the harmonic series diverges. So let's figure out what the limit of the ratio is as n goes to infinity of the series we want to know what happens over the series that we already know what happens. Okay. So here I have a top fraction divided by a bottom fraction. So I'm going to leave it as the top fraction multiplied by the reciprocal of the bottom fraction. What's going to happen is that n is going to flip all the way up to the top and just be multiplied by that 8. At this point, we want to know what this goes to as a sequence. There's a couple different ways you could do it. You could just treat it as a function and look at the horizontal asymptote. You could use L'Hopital's rule here because we have infinity up top and infinity on the bottom. There's a bunch of different things that you could do. Let's do L'Hopital's rule because we probably haven't done that in a while. So remember, L'Hopital's rule is as long as the top and the bottom go to either 0 or infinity, then you can take the derivative of the numerator and the derivative of the denominator separately. Okay, so again, my handwriting's bad, sorry. The 8n just goes to 8. 6n would go to 6 as the derivative. This is 5n to the 1/2, so we multiply that 1/2 on the 5, and then we take 1 away from the exponent. This negative exponent I can bring to the denominator of that little fraction there and write it like this. So just moving that n to the negative 1/2 into the denominator below the 5 and rewriting that as the square root of n. Now if I take the limit as n goes to infinity, this denominator blows up to infinity, which makes this fraction go to 0, which means that I just get the constant 8/6. Okay. Now, hopefully, you would have that worksheet in front of you and you would look up, well, what happens when the limit comparison test gives me a positive number as the limit of that ratio? I'll just kind of give it away here, or hopefully you remember, but remember that if this limit comes out to be a positive number, that means that those two series are intertwined. They're the same. So if one diverges, the other diverges. So our series diverges since the series 1 over n diverges and the limit of our series over 1 over n came out to be a positive number by the limit comparison test. All right, I know my handwriting is really bad. Again, sorry. Our series diverges since the series 1 over n diverges and the limit of the ratio of our series divided by the 1 over n series, that came out to be a positive number. By the limit comparison test, we know this is true. So is that one all right? I feel like I spent 10 minutes on an easy question. But does that make sense? Is there any questions? about how that one worked? Okay, great. I'm going to go with no. And let's move on to the next one. The next question is asking us to use the ratio test to determine if the series converges or diverges, or state that the test is inconclusive. So for this one, we have the series n equals 1 to infinity of 8 to the n over n factorial. And we're using the ratio test. All right, remember the ratio test is that limit as n goes to infinity of the absolute value of the n plus 1 term over the nth term. This is going to converge to something, and then based on that something, we're going to get some answers on whether our original series converges or diverges. So let's plug it all in. I'm going to go ahead and write this as the n plus 1 multiplied by the reciprocal of the nth. So we're going to do 8 to the n plus 1 over n plus 1 factorial multiplied by the nth term flipped over is going to be n factorial divided by 8 to the n. Still all inside of an absolute value. We want to simplify this down, and we're going to use the same tricks that we've been doing for a while now with the ratio test. Let's worry about the 8 stuff first. I have an 8 to the n plus 1 in the numerator, and then just an 8 to the n in the denominator. Those two things are going to cancel out to just be an 8 to the 1. The other thing that I have floating around is my n factorial and my n plus 1 factorial. For this, we're using the definition of factorials. This n plus 1 factorial I could rewrite as n plus 1 times n minus 1, n minus 2, n minus 3, all the way down to 1, or I could just cut it off here at the n and write it as n plus 1 times n factorial. This and the thing right below it are exactly the same, and now I can cancel out the n factorials on top and bottom. All I have left over is the 8 in the numerator and the n plus 1 in the denominator. Remember, we're taking the limit as n goes to infinity. If I let n go to infinity, that means this denominator goes to infinity, which means that this whole ratio just goes to 0. Don't forget that the ratio test, this limit that we get is what we call rho, or funny looking p. And then based on what this is, we have 3 different answers that we can get from this. When the rho is less than 1, which is what we have, then we have absolute convergence. However you spell that. Absolute convergence. If the rho is equal to 1, the test is inconclusive. If the rho is greater than 1, then it diverges. All right, is that one all right? Ratio test? Does that make sense? Awesome. You guys want to talk about something really fascinating real quick? Just to get away from this. Let's look at this series. 1 plus 2 plus 3 plus 4 plus 5 plus forever and ever and ever. So the infinite sum, n going from 1 to infinity of just n. All right. The question is, what does this series converge to? So what do you guys think? 1 plus 2 plus 3 plus 4 plus 5 forever and ever and ever. That as a series, does it converge? If so, what does it converge to? I know this is new. I don't think I've ever asked questions of you guys. Ah, come on, anybody? 1 plus 2 plus 3 plus 4 plus 5 plus 6, all the way to infinity. In real life. What's that? Okay. Good, right? To infinity. We would think, right, that would blow up to infinity? What if I told you it doesn't blow up to infinity? What if I told you that this infinite series actually converges to negative 1/12? And not only does that sound crazy, which I know, but there are math and physics books out there that have this, just stated as if it's true. This is what's called the golden nugget in math. And there's all kinds of controversy and people that say one way or the other, whether it's true or not, and all kinds of proofs. But in real life experiments, if you have some kind of experiment where the series 1 plus 2 plus 3 plus 4 plus 5 goes on all the way to infinity, and you substitute that series out with negative 1/12, the physics just works. Crazy, right? Isn't math cool? Just to show I'm not making this up. Golden nugget. See? Golden nugget. Negative 1/12. Fantastic number. 1 plus 2 plus 3 plus 4. Negative 1/12. And then they have some like proof. A little bit of a mini proof on why it comes out to be negative 1/12. You guys can read through that if you're super curious. Is that not the coolest thing ever? No, just me. That's fine. You guys don't have to be excited about the same stuff I'm excited about. It would only give you extra credit points. But, if you're not interested in extra credits. This is why math is so confusing. Yeah, I agree. Math for you guys probably got weird like right around the time you started going into calculus. As soon as numbers started disappearing, that's when math starts getting weird. You want to see some other weird things? All right, I'm on a tangent now, I know. But this is so cool. If I were to ever get a tattoo, this is what I would get a tattoo of. So this is what's called the beautiful equation. So the beautiful equation, e raised to the I pi plus 1 is equal to 0. The reason this is called the beautiful equation is because it has the most important numbers. Pi, of course, super important. E, very important. I, the imaginary number, important. 1 is the kernel for multiplication. 0, the kernel for addition. All very important numbers. So just looking at this equation, it probably doesn't look all that fascinating until you really dive into it. So E is this infinitely long number. I don't know exactly what it is. 2.78 something, something, something. Forever and ever and ever and ever. We're going to take that number and multiply that by itself in imaginary square root negative 1 times 3.14 forever and ever and ever and ever and ever. And somehow, this crazy thing comes out to be negative 1. So you take a positive number and multiply it by itself an imaginary number of times by pi, and it comes out to be a negative 1. Cool, right? All right. That's enough of tangents. We'll go back to the thing. Maybe. I've lost... Oh, did I close out of the... Oh, there it is. Let's go back to the test. Okay, we are on number 6 here. Determine if the alternating series converges absolutely, conditionally, or diverges. So we're looking at this alternating series, n equals 1 to infinity, -1 to the n, that's the alternating part, and then 1 over square root n as the u part of the alternating series, the part that's always positive. All right, this is an alternating series, so let's use the alternating series test just to get some practice with it. So the alternating series test, there are 3 things that have to happen for this series to converge. The first thing that has to happen is that the u sub n's, and by the way, the u sub n's for this example is 1 over square root n. These u sub n's always have to be positive. They always have to be greater than 0. As I plug in n going from 1 to infinity, I hope it's pretty obvious that 1 over the square root of a positive number is always going to be positive. So we'll just check that one off because that one's always going to be true. The second thing that has to happen is that your u sub n's have to be non-increasing. All right. Remember that non-increasing means that it could either be decreasing or it could remain constant. This one I'm also not really going to prove all that much because I hope it's obvious. As I keep plugging bigger and bigger numbers in for my n, it's going to make the denominator bigger, which is going to make the whole thing smaller, so it is decreasing. The last thing that you have to show for the alternating series test is you have to show that your u sub n as a sequence converges to 0. This one I also hope is obvious, because if I plug n to be infinity, n as a sequence, the denominator blows up to infinity, which makes the whole fraction go to 0. All 3 of these things are satisfied, which means by the alternating series test, our series converges. Now, the question, though, is asking a little bit more than just does it converge. It wants to know, does our alternating series converge absolutely, converge conditionally, or diverges? We've already eliminated diverges because we do know that it converges. We just don't know if it converges absolutely or if it converges conditionally. Remember that for something to converge absolutely, not only does the series itself has to converge, but the absolute value of that series has to converge as well. So we're going to test for absolute convergence by looking at the series of just 1 over square root n, without the alternating part because the absolute value would make that part go away. So now we have to use another test to see whether this converges or diverges. You don't really have to do too much. I hope that you can just look at this and tell me whether it diverges or converges. This is going to diverge, and the reason it's going to diverge is because of the p-series. The exponent in my n is 1/2, and remember that this only converges when the exponent is bigger than 1. So for us, it's going to diverge. So because the absolute value diverges, it does not converge absolutely. This is going to converge conditionally. So thus converges conditionally. Okay, is that one all right? Does everybody understand the difference between absolute convergence and conditional convergence? Everybody okay with the alternating series test? Any questions about any of that? Okay, cool. see what else we got. Find the interval of convergence. We already did an interval of convergence question already in section 7, that number 16 question that we did. So I'm going to skip this one. Just know it's the same thing. You could probably do the root test for this one, but ratio test would also work. We've already done one of these as well. Finding a Taylor polynomial. We did a Maclaurin series instead. So I guess really we did like number 9 here, the Maclaurin series. But this is the same exact thing. So this is that you would have the Taylor series formula in front of you. You'd have to take some derivatives. We would only have to go up to order 3, so we'd have to go up to the third derivative, and then plug in 1 into all of those to get the coefficients, and then substitute that stuff back in to get the Taylor polynomial. Do we feel okay with this, or do you want to see this one worked out? Does anybody want to see this one worked out? I can do it fairly quickly. Oh, you're really quiet.
I am.
Okay, yeah. I got some other yeses, so we want to see this one. Let's do it. Okay, so here we have the function. F of x is 1 over 4 minus x. And then we want our centering point to be a is equal to 1. So we're trying to find the Taylor polynomial up to order 3. So first we would go to our notes and we would grab the formula for the Taylor series. That's the sum in going from 0 to infinity of the nth derivative, or I guess they usually do k's, but nth derivative, plugging in the centering point divided by n factorial times x minus that centering point to the n. So this is just the formula for Taylor series. Okay, if we are going to order 3, that means that we have to have at least up until the third derivative of our function to figure out what our coefficients are going to be. Our function is this 1 over 4 minus x. I'm going to think about this as 4 minus x to the negative 1, just because that'll help me do some derivatives. Another thing that we need to do with these is we also need to plug in 1 into each of those. We'll do that after we find the derivatives. Okay, so the first derivative, we're going to have to do a chain rule here. We're going to bring down the negative 1, leave the inside alone, and then take 1 away from the exponent to make it negative 2. But don't forget to also multiply by the derivative of the inside, which is going to be another negative 1. So simplifying it down, these two negative signs are going to cancel out. We get 4 minus x to the negative 2. All right, for the next derivative, the second derivative, we're going to bring down the negative 2, leave the inside alone, take 1 away from the exponent, multiply by the derivative of the inside. The negative 2 and the negative 1 are going to multiply out to be a positive 2. All right, and then one last time, we're going to multiply down by the negative 3, take 1 away from the exponent, multiply by the derivative of the inside, combine the negative 6 and the negative 1 together. Okay, so that was just taking the derivative 4 times. We need these derivatives, but only at the location A, and remember A was 1, that was just given to us in the question. So let's plug 1 in for all of these. When I plug 1 into the function itself, I get 4 minus 1, which is 3. 3 to the negative 1 is 1/3. If I plug 1 into the second derivative, 4 minus 1 is 3. 3 to the negative 2 is 1/9. If I plug that into the second derivative here, I have a 2 floating around. And then it's going to be 3 to the negative 3, which is going to be 1 over 27. And then I have a 6 floating around. 3 to the negative 4 is 81. So these, 1/3, 1/9, 2/27, 6 over 81, that probably simplifies down, doesn't it? A 3 will go into both of those, so 2 over 27. These are going to be the coefficients of the Taylor series, or in this case, the Taylor polynomial. So we can go ahead and start plugging stuff in. Okay, so our Taylor polynomial of order 3. It's going to be the first term of the Taylor series. The first term of the Taylor series is plugging in n to be 0. So it's going to be the original function at 1, that was the 1/3, divided by 0 factorial. 0 factorial is just 1, so that doesn't do anything, times x minus 1 to the 0 power, which is just 1. So for my Taylor polynomial, I'm just going to have the constant 1/3 out in front. Plus, plugging in n to be 1. It's the first derivative at 1. That came out to be the next coefficient, 1/9. That's going to be divided by 1 factorial, which is just 1, times x minus 1 to the 1. All right, that plus the next term, n to be 2. So that's the second derivative at 1. That was the 2 over 27. That is going to be divided by 2 factorial times x minus 1 squared now. And then finally plugging in n to be 3, we have another 2 over 27. This time it's going to be over 3 factorial, and then it's going to be x minus 1 cubed. And we can just stop there because they were asking us to find the Taylor polynomial and not the Taylor series, so we don't have to multiply this stuff out any. We can kind of combine some terms together to make it look a little bit neater. So the 1/3, I'll leave this one as 1/9 times x minus 1. 2 over 27 divided by 2 factorial is going to be 1 over 27. This is times x minus 1 squared. These two fractions together, I think it's 1 over 81, it looks like. It's going to be x minus 1 cubed. So this would be my Taylor polynomial of order 3 of the function, I forget what it even was at this point, 1 over 4 minus x. And I hope you understand why this is important. So I know in the video that I made already, I did some stuff with Desmos. We were graphing this stuff out. I kind of want to do it again, just real quick, just to like really reinforce the whole purpose of Taylor series. So if I were to graph out the function itself that I started with, 1 over 4 minus x, that gives me this graph. I want to compare this to my Taylor polynomial I just had, which was 1/3 plus 1/9 times x minus 1 plus, what was it, 1 over 27 x minus 1 squared, and then plus 1 over 81 x minus 1 cubed. Cool. If we look at these two series, these two functions, notice how drastically different they are, except right around here. The reason that it's only the same right around here is because that has to do with that interval of convergence. Just looking at this graph, the interval of convergence looks like it's between 0 and 2. It may go out a little bit further than that, but just off of first instincts, 0 to 2. So this Taylor polynomial of order 3 almost perfectly approximates our function between that interval of convergence. The reason this is important is because a lot of time in math or physics or whatever field that you're using the math in, we don't really care about what happens to this function other than on a very small interval. So if we could use Taylor series to approximate a complicated function on that interval, then that's really nice. Okay, great. Is this all right? Is there any questions about that?
No, thank you.
Sure. Let's go back to the test here and see if there's anything else. 9 is the same thing, right? That's just the Maclaurin series. So you just do the same stuff. 10 I said to skip. Let's talk about 11 a little bit. So I won't actually do this one, but let's just talk about it. Use series to estimate the integral's value to within an error of magnitude less than 10 to the negative 3. This integral is impossible to do by hand. There is no way to find the antiderivative of this thing. But what you could do is you could find the Taylor polynomial up to some order and then just integrate over that Taylor polynomial between 0 and 0.3. In fact, that is what your calculator kind of does when it is approximating the Riemann rectangles when it does the integral in the calculator. 12 I said to skip, so we can ignore that. And then there's a bonus question down here. The remainder estimation theorem. So that was in one of the videos that I made. This has to do with the integral test a little bit, and using the integral test to kind of, approximate some stuff. But we can ignore that one. So is everybody okay with this practice test? There is another practice thing that I have up in Moodle. So if we have time on Thursday, and if there's enough of you that come Thursday, we can look over that, this practice stuff Word document here. And then, of course, if you guys have any other homework questions, we can do those on Thursday as well. Before I let you guys go for the day, is there any last questions about the Chapter 10 test coming up? Okay, great. Let's get out of here then. Thanks for coming. Thanks for sticking around for so long and listening to my rants some. And hopefully I'll see you guys on Thursday.